Alright guys, so today we're going to talk about thin film interference, and just like all the other interference that we've discussed, the basic equation we always start with is delta L equals m lambda. So, just like everything else we've talked about, delta L stands for the path length between two rays of light that are going to interfere with each other. Lambda is the wavelength of that light, and m is going to represent either a whole number of wavelengths or a half number of wavelengths. As always, if m is a whole number, that will represent constructive interference, and if m is a half number, that will represent destructive interference. So before we start talking about how we're going to calculate delta L for thin film interference, hopefully you already watched the Pivot Interactive on reflection, because we're going to talk a little bit about that because it's important for this concept. Okay, so here I've shown an interface between air and water, and remember air has an index of refraction of 1 and water has an index of refraction of 1.33. So let's say that we had a ray of light coming down through the air and it hits that interface, and of course some of that light is going to reflect off. When that light reflects off that air-water interface, because it's moving through a faster medium and reflecting off a slower medium, that behaves as a fixed boundary. And so this reflected wave is going to have a phase shift. The wave's going to be inverted, just like you saw with the spring. But if I had light coming up through the water and reflecting off that interface, that wave is traveling through a slower medium and reflecting off a faster medium, and that behaves as a free boundary. So this reflected wave would have no phase shift. And that phase shift becomes important when we start talking about the path length difference for thin film interference. Alright, so here we have a thin film of water sitting on top of glass with, of course, air above the water. This situation is what I call a progressive. I don't know of anybody else that calls it that. But the reason I call it that is because the index of refraction gets progressively larger as you move down through from air to water to glass. So we see this red ray of light incident on the air-water interface. And so, of course, some of that light is going to reflect straight back up off that interface. And I'm just going to show it over to the right, even though it would be coming straight back on itself. But then also, some of that light would go down through the water, and then it's going to reflect back up. Once again, it'd be right on top of itself. I'm just showing it off to the side. And then it's going to come back out. And so once again, all these rays are going to be right on top of each other. So those two reflected rays have the opportunity to interfere with each other, either constructively or destructively, depending on the path length difference. The other thing we have to realize is that the light that reflects off the air-water interface is going to be inverted, but the light that reflects off the water-glass interface would also be inverted. And so, since it's inverted at both interfaces, we can actually just ignore it completely. And so in this case, our path length difference, delta L, would just be 2 times the thickness of the film. And then remember, we always set that equal to m times lambda. Now, another important thing to realize is that the path length difference happens inside the film, so this lambda has to be the wavelength in the film. So let's say, for example, that this was red light with a wavelength of 640 nanometers in the air. Then the wavelength inside the water would be 640 divided by the index of refraction of water, which comes out to about 480 nanometers. So for a problem like this, we're going to care about the wavelength in the film, which in this case is the wavelength in the water, which will come out to 480 nanometers. So let's look at some situations for constructive and destructive interference. So let's say we wanted to know, what does the thickness of the film of water have to be in order to have m equals 1 for that first order constructive interference. Then we set 2 times the thickness of the film equal to 1 times the wavelength in the film. And so what we would see is that our thickness would have to be half a wavelength, 480 over 2, or 240 nanometers. You could find other thicknesses for constructive interference by using m equals 2, m equals 3, m equals 4, etc. But let's say we want to find out about destructive interference. So to find a thickness that will give destructive interference, m could equal 1/2 in this example here. Of course, we could also do 3/2, 5/2, 7/2, etc. So in this situation, I have 2 times the thickness of the film equals 1/2 times the wavelength, which is 480 nanometers inside the water. And so what I will see then is that T ends up equaling 480 divided by 4, or 1/4 of the wavelength inside the film. And in that case, that's going to be 120 nanometers. All right, next we're going to see what happens if we have a little bit different of a setup with our 3 indices of refraction. All right, so here we have a setup that I call the sandwich. Once again, I don't know that anybody else calls it that, but that's just the way I think of it. And the reason I think of it is in this case, oil is our film, and notice that it has the highest index of refraction. The index of refraction above it and below it are less than the index of refraction of the oil. So the sandwich is when the most extreme index of refraction is your film in the middle. It could be the other way around as well if you had the smallest index of refraction in the film and larger values on either side. So this is going to behave a little differently. So this time I will see that my ray that reflects off the air-oil interface, that is going to be a fixed boundary, so it's going to be inverted. But the ray that reflects off the oil-water interface is a free boundary, so it will not be inverted. So this time when I do my path length difference, delta L, that is actually going to be 2t minus half a wavelength, because when that wave gets inverted, it's like it's traveled half of a wavelength. And so for delta L then, since one is inverted and the other is not, we're going to use 2t minus lambda over 2. And that's going to equal m lambda. And once again, it's important to remember the wavelength is going to be lambda in the film. So in this case, that's going to be lambda in oil. So let's say that the wavelength in air was 630 nanometers. Then the wavelength in the oil would be 630 divided by 1.5, which comes out to 420 nanometers. All right, so let's say we want to find the thickness of the film for our first order constructive interference, m equals 1. So I have 2t minus wavelength over 2 equals 1 times the wavelength. And so in this case, that would mean 2t would have to equal 420 plus half of 420, which would give me 630. And so the thickness of that film ends up being 630 divided by 2, which would be 315 nanometers. Okay? So that comes out to 3/4 of the wavelength of light in the film, and that gives us our first order constructive interference. But remember, we also get constructive interference when m equals 0. So in that case, I'd have 2 times the thickness minus the wavelength over 2 equals 0 times 420, which is just 0. So 2t equals 420 over 2. So t is 420 over 4. So in that case, my thickness is going to be 1/4 of the wavelength in the film, 105 nanometers. Of course, if I want to find destructive interference, then I'm going to set m equal to 1/2, 3/2, 5/2, etc. And that will allow me to find the thickness of the film for destructive interference. And what you'll notice is that the thicknesses end up swapping in this situation. compared to the progressive situation we talked about a minute ago. Now for all these situations, we've simplified the math by having the ray go straight in and straight out at an angle of 0 degrees to the normal. And that's how all the problems should be on the AP Physics 2 exam, so that's all we're going to focus on. Of course, if they came in at a much different angle, then your path length difference would not just be twice the thickness of the film. You'd actually have to do the trigonometry to figure out the path length as it went along the angle. But we should not ever have to do that for this class. All right, guys, that's it for thin film interference. I hope it made sense. We'll go over any questions you have on Monday.